Okay, good morning, everyone. As usual, how did you do with your homework? Do you have any question about it before I get started? Okay, 67 and 28 and 12. Okay, I write them down. Very good. Right, so we start with number 12 and we proceed. So here is the question, number 12. Let me pick it up. In number 12, they give us the values of the derivative as a table. And then they ask us to find the derivative of new functions. So we have the following: 1, 2, 3, 4, 5. So for those input, so they give us the derivative of f for some values. So it's 3, 5, 2, 1, 4, 3, 5, 2, 1, 4. And another function, g prime, and it's 2, 4, 3, 2, 4, 3, and 1, 5. Okay. And the question is, find the derivative. So they use what I called yesterday the Leibniz notation. Find the derivative with respect to x of the sum f plus g evaluated at the point x equal to 1. Okay, so that's what they want us to find. First, let us make sure we understand here the table. So here they did not graph the function. They give us the derivative at some point. So for example, according to this, the function f at the derivative at 1 equal to 3. It means the slope is equal to 3. Like in this case, the g prime at 1 is equal to 2. It means the slope at 1 is equal to 2. And the question is, find the derivative at x equal to 1. Okay, the way we evaluate the derivative at a fixed point is first, we evaluate the derivative at any point. So what's the derivative with respect to x of f plus g? So first I said yesterday, if you remember, I said if we have two functions, we can create a new one, which is the sum of the two old one. Then this new function will have a new derivative because it have a new slope. So the derivative of that is the derivative of x of f plus the derivative with respect to x of g of x. In other words, if you're using the prime notation, it means the derivative of f plus g is the derivative of f plus the derivative of g. So remember, that's nothing more than a notation for the derivative. Now, they want us to find at x equal to 1. So they want us to evaluate everything at a specific point. That's what this notation means. So this means at x equal to 1, it means they want the derivative. Sorry, I'll forget about that. Okay, so now we want the derivative at x equal to 1. At x equal to 1. So this is nothing more than the derivative of f at 1 plus the derivative of f at 1. So for any x, the derivative is f prime g prime. At 1, it means f prime of 1 plus g prime of 1. And now we just pick up values from the list here. At 1, it's 3. This is a 2. So that's 3 plus 2, which is equal to 5. Okay. All right, now let's look at your second problem, which is number 12. We did that. Sorry, number 28. So try to go by increasing order. So number 28. Okay. And this is the function g of t equal 6 times the square root of t. And the question is to find the derivative. Okay. Remember yesterday we said to be able, we have one main rule for the derivative of functions so far, which tells me that if a function, we're gonna call the variable x, is x to a power, like x squared, x cubed, square root of x, then that's the derivative. Okay, that's one of the main rules. So now we need the derivative of g. So how shall we do that? We have to rewrite this. So we have always we rewrite. So usually I tell my student derivative doesn't like the square root, just like exponent. So we have to rewrite, no more, no less so far. 6 times the t become t to the power a half. Okay. Now I use the rule. And then yesterday also we saw a rule tells me that if you have a function f, and if you stretch it, multiplied by a constant, you're creating a whole new function because you're stretching the whole old function. So you're changing the slope. But what's this new slope? It's you pull the constant out times f prime. So what is g prime? Basically the constant, you drop it, and then you find the derivative of that. So this is equal to 6 times. The derivative of this is a half, that's the n. So from here to here, my n is a half, times t is my variable here, to the power n minus 1. So this would give me 6 times a half is a 3, t to the minus a half. In other words, or 3 to the power over t to the half, it means 3 over the square root of t. So anytime I have the square root term, whether to the half, whether to the third, anytime I have that, we have to rewrite it in this format. Once I rewrite it, I can use the formula verbatim. And now we look at 67 and then 78. Okay. 67. So here is 67. Finding slope location. So we have a function which is given by f of x equal 4 times the square root of x minus x. Okay. And the first question is find all values of x where the tangent is horizontal. Okay. So why we always ask those questions? The tangent is horizontal. Why those are important? Let's see if we can graph this function. And if I can graph it, I will we'll talk about which point I'm interested in because I don't know the graph of this function by heart. So if we graph this function, so let's go back here. Okay, so this is 4 times square root of x minus x. No, that's not what I want. Okay, so that's the function. So let me graph it a little bit. So that's the graph of the function. Let's zoom out of it. Okay, so that's the graph. So I want to know when the tangent is horizontal. So according to this graph, it's horizontal right there. Why we care about them? Because as you realize, the function peaks at this point. So if I want to know the maximum value obtained by this function, I definitely would like to know this point. And that's the point we are really going after. So it looks like it's 4, 4 from the picture, but the picture, that's not what we rely on. So the way we're going to do it, we will find the value of x where the slope is 0, and then we proceed. So that's why we care about those points. So let us start doing this. So we're going to find the tangent is horizontal, which basically we find this derivative equal to 0 and solve for x. Now, why the derivative? Because this is the slope of the tangent. It means we set the slope of the tangent equal to 0 and we solve for x. Okay, so we have two things to do. We have first to compute the derivative, then we have to set equal to 0. So let us compute f prime. Okay, I cannot compute f prime yet because it's not in the proper format. So I'm going to cancel that and I'm going to go back to f and rewrite it in the format that is easy for us. F x to the power a half minus x. Okay, so what is f prime? F prime is 4 times a half x to the half minus 1 minus 1. So this is equal to 2x to the minus a half minus 1. It means 2 over the square root of x minus 1. Okay, now we need to solve. It means I want to find which x I should put here that will give me a 0. So now I'm setting the slope. So this tells me at every point, that's the formula for the slope. Now I'm going to set this equal to 0 and we're going to solve for x. All right. Now how do we solve for x in here? Okay, how we solve? So I will put the 1 from this side and then we cross multiply. I mean, that's the only way we can do it. So if we cross multiply, this will give me 2 equal the square root of x. Now I need to solve for x. I square both terms and I will get x equal to 4. Okay, so the slope is horizontal for x equal to 4. Now if I want, so these are the value of x. Now if I need the point, okay, I need to find the point for f of 4. That's where it will be horizontal. Now what is f of 4? I go back, let's see, my function was, I'll write it in front of us, is 4 root x minus x. So if I want f of 4, it's 4 times 2 minus 4, which is equal to 4. And that's what we actually saw on the graph. That's really, you know, it's such a simple point, not simple, I meant that's such an easy point, we were able immediately to solve it on the, to see it on the graph. And that's really the point we are after. Okay. Now part B. Please ask questions as you move on. Those type of problems are going to dominate the course in some ways, you know, because as you realize, it's their importance. It's really where the function reaches its maximum value. That's why we care a lot about this point. All right, now we're going to do part 2, or B if you want.
I have a question real quick.
Please, go ahead.
So where it says f, the point is at f and f of 4 and f of 4. So would that mean whatever x you get is going to be the x and the y basically? Because yes, it's always going to, okay.
Yeah, I mean, I think I understand your question. This is the x value. Remember when we graphed the function? Remember how we graphed it?
Yes.
Yeah, so you know how it turned out to be something like that. In a way. And that's the point I want. So that's what I want.
Oh, okay.
Are you with me?
Right. Yes.
That's what I'm after. Now, the setting the slope 0 gave me that this point, its x coordinate is 4. So what's the other coordinate? This is a point onto, this is the graph of the function. This is 4 root x minus x. That's the graph. So if I have the 4 here, then the y value, if you want to call it, is f of 4, which is equal, happen to be 4. I mean, it doesn't have to be, of course. Okay?
All right.
That's the point.
Thank you.
That's the point I'm after. All right.
Okay.
Okay, so now the second one, the second question is, find all point on the graph at which the tangent line has a slope minus a half. So we want to find a point, find the x, where slope of the tangent line is minus a half. So this is hard to even visualize on the graph because it's somewhere in here, one of those points, because the derivative is negative, but it's like this point where I could exactly spot it on the graph. This one I really don't. So we just have to do it algebraically. First we have to do it algebraically, but this one I even don't know where it is. So we're gonna set the derivative equal to 0, but that's the slope, so that's the slope, equal minus a half, and solve for x. Okay. Now we already evaluated the derivative. So the derivative, we evaluated that, it was 2 over the square root of x minus 1, and we're gonna set this equal to a negative half. All right, so again, we're going to isolate the term where we have x. So we're going to add 1 both sides. So we're going to add a plus 1. And this would give me, this is equal, minus a half. We add 1, we get a half. And now we do the same thing. We're going to cross multiply. So we can solve. So we cross multiply. And we get square root of x equal to 4. It means square both sides, x equal to 60. Okay, so somewhere, most probably it's going to be here, according to the graph, that's the 16. And if I go down here, it means right here, if I compute the slope, so this is, the slope is minus a half, that's the slope. And the point is 16 and f of 16. So let us compute f of 16. So f of 16, that's now I'm after the point. It's 4 square root of 16 minus 4 because, no, not, sorry, minus 16 because f of x is 4 root x minus x. So minus 16, which is going to give me 4 times 4, which is going to give me 16 minus 16, which is equal to 0. So 16, 0, that's the point. Okay, so according to my graph, so this has to go. I was wrong here. So that's my 16 right there. And that says 16, 0, and it's right here where the slope is minus a half. So now after I know the y value, the slope here is minus a half. Okay. Questions before I go on to number 78? All right, so let's look at number 78. What is this? So here they gave us the graph of two functions, f and g. And and they create a new function. So in number 78, we have the following. They gave us the graph of two functions f and g. Now I will pull a book. I will get the book and see if we can just see on the book what's happening. And then they create a new function, which is f plus g. And the question is find f prime of 2. Okay, so that's a new function. So first, what is f prime at x? Since this is the sum, so for any x, so that's a totally new function. It's what the derivative of f at x plus the derivative of g at x. That's the rule. So if I want it at 2, it means I need the derivative of f at 2, and I should add to it the derivative of g at 2. So now, do we know f prime at 2 and do we know g prime of 2? That's where I have to go back to the picture and see if we can do that. So if I can do it using the book, fine. Otherwise, I will try to reproduce the picture. Okay, I think we can do that. All right, so let's look at the graph very carefully. This is my f, which is the black one, and the g is the red one, and I need the derivative at 2. So this is my 2 right here, and this is my function. So what's the derivative at 2 of f? Is this easy to figure out? Back to you guys. So who can give me the derivative at 2? Okay, Luke is telling me 3. Okay, why? Because the derivative, I think, no way under the sun. Minus 3. Yeah. Okay, all right. So to find the derivative of f at 2, this is a linear function. This is nothing more than the slope of this line. That's the derivative, okay? So the derivative, everybody tells me, you can take 2 points. Those are clear points, and find the slope. So the slope is, okay, very clearly, the slope here is minus 3. So we know f. Now I know I want g. Okay, so g prime at 2. So this is g. I go back this graph now. Okay, I want the slope here. And the slope here, it is 1, right? Am I goofing? No. So for g, it is 1. So this is 2. I go back to the graph itself. So that's the point. And what's the slope of this line? If you got by 1, it's equal to 1. So now I have f prime, which is negative 3, and I have g prime, which is 1. So this is going to be equal to negative 3 plus 1, which is negative 2. Okay. And now, we can, if we look at 79, just to make sure in 79, for example, they give us a new function and they call it g, which is 3f minus g, okay? Again, this is a new function obtained from those 2 old functions, and they want g prime at 2. Okay, so first we find g prime at any point. That's at any point. That's really the rules which telling me that. Now I zoom in at a specific point. And then we're done. That's 3 times minus 3 minus 1, which is going to give me minus 9 minus 1, which is equal to minus 10. End of the problem.
Professor, I have a question.
Of course, go ahead.
Let's say that was to be 3f and an x, and then it's 2x. How would you go about doing that?
Oh boy, you have to repeat your question.
Well, so, like the last part where it says
this one?
Negative. Yeah.
Yeah.
For the last part of it where it says g2.
G prime.
What if it was like 2 and an x? How would you go about solving that?
Can you put it on chat? I honestly cannot follow the question.
Yeah. Okay.
Which one you're changing? Unless anybody can help me. Which one you're changing? Are you changing G? Are you changing 2? That's what I'm not following.
G.
So what's your G?
2.
2.
Yeah.
So G of X is 2?
Yes.
It means G prime is 0.
Okay.
I'm honestly trying. Is it 2x? That's what I read. So if G of X is 2x, then G prime is, if G of X is 2x, G prime is, this is a constant, which is a 2. The derivative of X is 1.
Oh, okay.
Am I getting anywhere close to what you want?
Yeah, that was it.
Thank you very much. Okay. All right. So any other questions before we proceed further? Okay, so we're gonna keep along the same line, and we're still in section 3.3, and we're going to develop the derivative of the exponential function, e to the x. So the derivative of we're still in the same section. F of x equal e to the x, the exponential function. All right. So we first graphically a little bit. So we're going to sketch the graph of e to the x and then sketch its derivative, just for practice this idea. So let us see how the graph of f of x looks like. So the graph of f, remember that x, e to the x never take on negative values. And when x takes large negative, the e to the x, so when x start taking minus 10, which is when e to the 10, it means the function is very, very small. So it goes and then it keeps going like this. So that's the exponential. And right here, it takes the value 1. Okay, so that's x. And that's f of x equal e to the x. Okay. So at least picture-wise, how does the graph looks like? Okay, so of f prime. So now I'm after f prime. So we're gonna go after the slope as usual. So first, the function is actually increasing. So the slope is always positive, 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 positive. So it's always positive. And how is the slope? Right here, as we realize, the function is almost flattening out. It means it's not really changing much. The slope is very small. It's almost 0. And then it starts getting larger, 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 larger. So if I'm going to sketch it right here, it is positive. So the values are here, but they are very close to 0. And then they go larger, 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 larger. So that's the derivative. That's the derivative. Okay, so it's very similar in the graph, but what is the derivative? So first, I'm going to focus on the derivative at 0. We're going to do this numerically, and then the derivative for any x. So first, let us find the derivative of f at 0. So this is f of x equal e to the x. Okay, step number 1, find f prime at 0 numerically. And I will make sure you know what this means. Okay, numerically. So what is f prime at 0? Okay, what is f prime? Let's remember the formula. F prime for any x, because once we start learning those rules, we forget the formula, which will not allow it. What's f prime of x? It's the limit of f of x plus h minus f of x. So that's the slope of the secant line as this goes to 0. So now I need f prime at 0. That's equal to the limit as h goes to 0 of f, which is e to the 0 plus h, minus e to the 0 over h. Okay, so this is equal to the limit as h goes to 0 of e to the h minus 1 over h. Okay, and now numerically, it means I honestly gonna pick a calculator and start evaluating this limit by letting h take smaller and smaller value. So I'm gonna make a table, and I'm gonna cheat a little bit. I'm gonna only take h positive, which is not correct. I should take both of them, but I'm cheating. So, and these are the slopes. So remember, those are the slopes of the secant line. And let us evaluate this. So I'm going to take some values, and I'm going to do it on my calculator right there. So I want h to become close to 0. So we're going to take like 0.1, 0.001, and zoom in a little bit more and see what we get. So you guys can help me if your calculator is next to you. So I'm going to take e to the power 0.1 minus 1, and I'm going to divide this by 0.1. So I'm getting 1.1 0.0517. All right. Now, let me zoom in a little bit more. So I'm evaluating this at 0.01. So what I'm doing is I'm taking e to the power 0.01, and I'm taking away a 1. And then I'm dividing this by 0.01. I'm getting 1.005. 0050. Okay, I will go one more. So I'm going to take e to the power 0.0001, for example. I take away a 1. And then I divide by 0.000. No, sorry. I'm going to divide by 0.0001. And I'm getting 1.000, I mean, tons of those. So it's obviously 1, 2, 3, 4, 5. So obviously, as those are getting close to 0, this is getting close to 1. Okay, so I did this purely numerically because that's the only way we know how to do it. So this is equal to 1. So it means the derivative at 0. So if I go to my graph here, at 0, this slope here, right there, this slope is equal to 1. Oh, sorry. The slope is equal to 1. So when I'm graphing the derivative, this also has to be 1. So this slope is 1, this is equal to 1. So that's the derivative at 0. Now we're going to find a formula for the derivative in general. So we're going to do that. We'll spend a little bit of time on it. Can I move on? You guys fine? Okay. So now let us find the derivative at x. It means for any value of x, what is the derivative? Okay. So now we're going to find f prime at x. Okay, what is the formula for f prime? So this is equal to the limit as h goes to 0. So I'm still working with the same function. My function is always e to the x. So it's the limit as h goes to 0 of f, x plus h, minus f of x over h. Means this is equal to the limit as h goes to 0 of f of x plus h means e to the x plus h minus f of x e to the x divided by h. Okay. So let us compute this. This is equal to the limit as h goes to 0 of the following. Now I'm gonna do a little bit of algebra to be able to figure out the problem. E to the x plus h, e to the x plus h, by using the law of exponent, I can write it as e to the x times e to the h. So these are the law of exponent. So it's going to become e to the x times e to the h minus e to the x over h. So my goal is to find the formula for that. Okay, so this is going to be equal to the following limit. I can actually pull out the e to the x, and I will be left with e to the h from here minus 1 over h. Okay, so let's see what this is equal to. We're almost done. h 0, I can rewrite this as e to the x times this expression. But now, if I go back to what I did a minute ago, right there. Okay, when h goes to 0, e to the h minus 1 over h become close to 1. So x is fixed now. It's h which is changing, h becoming close to 0. So when h becoming close to 0, this expression right here is actually becoming close to 1. So what I'm going to do, what I'm going to get is exactly e to the x. Okay. So, of course, it's a surprising result, to say the least. So what this tells me that if the function f of x, so this tells me that the derivative of the function on f of x equal ex is itself. Now the graph told me that the shape looked the same, but it has nothing to do. It doesn't mean they actually are the same. The graph tells me they have the same shape. The formula tells me that they are the exact same function. And that's really the importance of e to the x, and it's the e. I will show you if we take in a minute, if we take 2 to the x, it doesn't work. E to the x is the only function that you'll ever see such that have the property that the function and its derivative are exactly the same. There is no other function that have this property, only e to the x. So this tells me that if you have the exponential function, the derivative with respect to x of e to the x is equal to e to the x. Or if I use the prime notation, the derivative of e to the x is e to the x. That's the only function in math that have this property. All right, let us do some small exercises involving that, and then I will go back and I say, okay, what if we have another exponential function? It means with different base. If the base is 2, does it really follow the same rule? So we will see that in a second. But first, let me have some problems to make sure we get that. So, okay, please, if I turn the page and you are not ready, let me know. So now this is my problem. Problem is the following. Let f of x, so a simple example. Let f of x equal e to the x minus 2x. Okay. And question number 1, find the equation of the tangent line to the graph of f at, let us say, the point a equals 0. That's to make the algebra simple. So this is nothing more than the equation of the tangent line. All right, so let us pick up a little bit and see how the graph look like. If this makes, sometimes it's nice to know how. So this is e to the x, e to the x, and this is minus 2x. Okay, and let's see a little bit. So, oh, what a weird function. I should have graphed it. All right, looks a little, okay, so what do I want? So let us a little bit zoom out of it to have a better picture. And I want the slope to the graph at a equal to 0. So somewhere in here. So the only thing I get, that's a negative number. And let us find it. So I will, the graph seems to me look a little bit like that. And then it goes fast. All right, so I'd stop the screen sharing. So that's how the graph looks like. And I need the slope here. Okay, I need the slope, the tangent. All right, and then as you expect, I want that. All right, so let's do that. To find the slope, first we need the slope of the tangent is the value that the derivative take at 0. Very good. But now, first I have to find the derivative, and then I plug in 0 into the expression. So first I need f prime. What is f prime of x? Equal to, okay, the derivative of e to the x, it's e to the x minus the derivative of 2x, 2 is a constant. The derivative of x is 1 times 1. Okay, so that's the derivative. Now I need it at the specific value, which is 0. So that's give me the slope of the tangent line. So that's e to the 0 minus 2. Anything to the power 0 is 1. So this gives me minus 1. So my slope here, the slope is minus 1. Now I need the point. To find the point, I need, it's 0 and the value of the function at 0. So it means it's 0. At 0, the function takes the value e to the 0 minus 0. So it takes the value 1. Now I have a point. So this point right here is 0, 1. Now I have a point and I have the slope. So now the equation is, actually we have the intercept here, y equal minus x plus 1. Okay. Now question number 2 is, as you expect, I want to see where this function is bottoming out. Okay, so I really am after the place where the derivative is 0 because I want to find what this value is. As you guys realize, in this situation, the graph was not really very helpful, unlike the previous one where it was clear for 4. Here, this wasn't very clear where the function takes its minimum value. So part B is going to be find the value of x where the tangent line is horizontal. So find all values of x. According to graph, there is only one, but that's not necessary, where the tangent line is horizontal. It's horizontal. Okay, so we have to basically, we have to set the derivative equal to 0. And I repeat again, because this is the slope of the tangent line. We're going to set this equal to 0 and solve for x. All right, we evaluated the derivative a minute ago. So the derivative is e to the x minus 2. We're going to set this equal to 0 and solve for x. All right, e to the x minus 2 equal to 0. So we've learned at the beginning how to solve those. So first I isolate my exponential term, e to the x equal to 2. Once I isolate the exponential, then I say that, okay, then I take the natural log equal to the natural log of e to the x. And now I use the property that this had, ln of e to the x is x itself is ln of 2. Okay, so a value where picking it up from a calculator is almost next to impossible to know that it's ln of 2. So this was my graph like this. And now I don't know what's the y value. It looked like 0 from the graph, but I really don't know because it could be a little bit. So I know that it's bottoming up right here. That's the ln of 2. Now I want to see the y value. Is it a 0? I actually don't know. If it's not 0, I will change my graph. So now I need the point where this is happening. So I need the point. The point will have a coordinate 2, f of 2. Now I'm back to the graph. So let's compute f of 2 now. What is f of 2? Nonsense. Absolute nonsense. It's ln of 2, f at ln of 2. All right, so now let us compute the value of the function at ln of 2. So f at ln of 2 equal. Now my original function, let me write it here in front of us to remind you. My original function was e to the x minus 2x. Okay, and this is going to be equal to e to the ln of 2 minus 2 ln of 2. So e to the ln of 2 is 2 minus 2 ln of 2. So it's definitely not 0. It's definitely not 0. So the graph was a little bit misleading because it's going to be probably close to 0. So let me a little bit evaluate it just to have a feeling. Where am I? It's 0.6. So it's almost 0.613. So the graph was wrong, but I couldn't read the scale very well on the graph. So it's definitely not a 0. So the graph, give us an idea, but not really so much accuracy. So this point is going to be the ln of 2 and 2 minus 2 ln of 2. And that's really the point on the graph. Okay, so that's the e to the x. That's the only function where actually the derivative is equal to itself. Now, the minute I take 2 to the x, the derivative will not be 2 to the x anymore. I'll give you a feeling what's happening for 2 to the x, and later on in the course, we will learn the derivative of 2 to the x. We are not ready for it yet. So suppose I take the function f of x equal 2 to the x, and the question is, will the derivative be influenced by that? So I'm going to do verbatim. So let us find the derivative of f of x equal 2 to the x. I'm changing the base, and I'm taking 2 to the x. And I will do verbatim what I did before. It means that first I'm going to find f prime at 0. So that's my new function. And that's going to be the limit as h goes to 0 of f at 0 plus h minus f at 0 over h. So it means the limit as h goes to 0 of f of 0 plus h, it means f of h, my function, that's 2 to the h, minus 1 over h. And we're going to do that numerically. We're going to do that numerically, as I did before. So I need to find those values. So I will make a little bit my table. That's the h. These are those. And I will take some values and figure this out the best possible way. And so I'm going to compute 2 to the h. So it's 2 to the power, what is the power here? To the power 0.1 minus 1 divided by 0.1. So I'm getting 0.7177. Now, of course, I need a lot of values to be able to approximate. And that's 0.01 minus 1. And now I'm getting 0.695. I'm going to zoom in a little bit more. So I will have 2 to the power 0.0001 minus 1. And now I'm getting 0.69317. So it seems to be hovering around 0.69. Remember, it's 695, 693. So I cannot go to 0.7. I have to stick around 0.69, and that's what's hovering around it. So this value is almost 0.69. So watch the difference. When I took e to the x, the slope here was 1. When I take 2 to the x, which is actually 2 to the x, which should be a little bit less here, 2 to the x, so it have the same shape, but it's sloping class. The 2 to the x has a totally different slope, 0.69. And that's going to affect the derivative. That's really going to affect the derivative. E to the x is going to be the only function whose derivative at 0 is 1. Any other exponential function, whether 3 to the x, 4 to the x, any other one will not have a slope of 1. That's basically the only function. That's what makes the point, the e, actually crucial for us. So the derivative is going to be, now if I repeat the process I did a minute ago, so if I have the function f of x equal 2 to the x, and so this is my function, 2 to the x, and I repeat the process to find the derivative of it, I will get the limit as h goes to 0, 2 to the x plus h minus 2 to the x over h. And I do what I did before, meaning, what did I do before? I took this and I used the law of exponent to write it this way. That's what we did. And this will give me the following. I factored out 2 to the x. I was left with that divided by h as h goes to 0. And now this term is not 1 anymore. This term is almost 0.69. Okay, so I'm not finding exactly the derivative because I'm really approximating, but I give you the idea that what's really happening, why we will very soon find a real formula. So it's going to be almost 0.69 times 2 to the x. So it's not 2 to the x anymore. And what we will show very soon is that this 0.69 is nothing more than, it's the exact value is going to be the log of 2 times 2 to the x. So it's very different. So that's the only, so that's what makes e to the x really an important function for us. All right. All right, so that's the end for today. I would like to really make a comment here because that's a common mistake students do for those who have been seeing the derivative at the beginning. X to the n versus 2 to the x, or let us say e to the x, we have to be very careful distinction. This is a power function. So in this scenario, the power is constant. The power is constant, and the derivative is n x to the minus 1. In this case, actually the power is the variable, x is the variable, and the derivative is e to the x. So it's not, what I'm trying to say, that this is not, you cannot treat this like that. So it's not x e to the x minus 1. That's not the derivative of that. That's not a power function. That's a power function, and is constant. And here it's a variable. All right, so that's will do for today. Tomorrow we're gonna keep along the same lines and introduce more and more function as we move on. Okay, any questions before I let go? Any questions? Okay, so please keep working on my lab, keep practicing those problems, and meet me in my office hours if you have any questions. Bye for now.